Ever find yourself wishing you could just, hear that article you just saw flash across your screen? Or maybe generate a sound effect instantly?
Oh, definitely. Text-to-audio tech is moving so
It
fast.
really is. And today we're diving headfirst into a really exciting breakthrough, something that's pushing how quickly we can turn text into pretty lifelike sound.
Exactly. We're looking at a paper called Fast Text-to-Audio Generation with Adversarial Post-Training. It's by Zachary Novak and folks from UC San Diego, Stability AI, and ARM.
Right. And our mission really is to figure out how this new approach they call ARC, that's Adversarial Relativistic-Contrastive Post-Training, gets such a speed boost for text to audio.
Yeah, and crucially, how it manages to do that without some of the, let's say, usual downsides you see with other speed-up methods.
Okay, so the paper kicks off by mentioning seconds to minutes per generation. That's apparently the state of play for a lot of these systems.
That's what they point out, yeah. And if you think about it,
Well, yeah. Imagine trying to brainstorm music ideas or create sound effects on the fly if you're waiting minutes each time.
it just doesn't work. It
Yeah.
totally puts the brakes on any kind of creative flow.
So that speed bottleneck was a major hurdle they wanted to tackle.
Absolutely. For any kind of interactive tool where you're generating sound from text in real time, that kind of lag is just, well, it's a non-starter.
Right, so you need something much, much faster.
Exactly. The need was definitely there.
So before this ARC method, what were the main ways people tried to speed things up? The paper mentions distillation.
Distillation, yeah, that's a pretty common technique.
Yeah.
Think of it like having a really experienced, maybe slightly slower master model, the teacher,
Okay.
and it trains a smaller, faster student model to basically copy its results.
Ah, okay. So the student learns to do what the teacher does, but quicker.
Precisely. It tries to mimic the quality, but at a fraction of the inference time.
Makes sense, like learning the shortcuts.
Uh.
But I'm guessing it's not perfect. There are drawbacks.
There are definitely catches. One way is online distillation, where you train both together,
Right.
but that's super demanding. You need the resources to run like 2 or even 3 big models simultaneously, lots of memory, lots of compute power.
Oof. Okay, expensive then. What about offline?
Offline distillation avoids running them together, but first you have the teacher generate a massive data set of examples,
Mm-hmm.
and then you train the student on that pre-generated data. But creating and just storing all that data can be really resource intensive too.
Gotcha. And then there's this other thing mentioned, classifier-free guidance.
Yeah.
CFG. How does that fit in?
Right, CFG. It's often used alongside distillation. It's basically a way to push the model harder to stick to the text prompt and, improve the overall quality.
Still giving it extra hints.
Kind of, yeah. Extra guidance on what you want. But the paper points out a downside. While CFG can make the audio sound maybe better or more prompt accurate, it can also backfire a bit. It can make the results less varied, less diverse. Sometimes the audio can sound a bit oversaturated or artificial.
So a trade-off.
Yeah.
Better prompt following maybe, but less creativity or naturalness.
Exactly. It's often a balancing act. So yeah, the existing fast methods often came with these kinds of compromises.
Okay, so that sets the stage for needing a different approach. Which brings us to this adversarial post-training idea. How does that work?
So instead of a teacher model, this approach fine-tunes an already trained model.
Right.
It does this by setting up a sort of competition. The main model, the generator, tries to create audio that can fool another model called a discriminator.
A judge, basically.
Exactly, a judge. And the key difference here is that it learns by comparing its output to real audio data, not audio made by another AI teacher.
Ah, okay.
The goal is to push the generator to make more realistic audio, faster and fewer generation steps. Think of it like a super talented mimic trying to fool an expert listener.
So the mimic gets better by trying to beat the expert's ear.
Interesting. But didn't you say this hadn't always worked so well before, like in image generation?
That's a really important point the paper makes. Previous attempts using this adversarial idea for speeding up image models often only got like small gains, or they still needed to start with a model that had already been distilled. So it wasn't a purely adversarial solution from the get-go.
Okay, so the challenge was making this adversarial approach really work on its own, especially for something complex like audio.
Precisely. And that leads us right into ARC, Adversarial Relativistic-Contrastive Post-Training.
Which they describe as fully adversarial, no distillation needed, no CFG needed. Sounds like the holy grail. Let's break down those two parts. Relativistic adversarial and contrastive.
Let's do it. First, the relativistic adversarial loss, the AR bit. They're building on a relatively recent idea in adversarial training, but applying it specifically to text to audio.
How does it differ from the standard way? You said the generator tries to fool the discriminator? Right. In the standard setup, the generator makes something, and the discriminator just says real or fake. They're kind of judged independently.
Yeah.
But this relativistic loss changes the game. It forces a comparison. The discriminator looks at a pair of audio samples, one real, one generated by the model, but both based on the exact same text prompt.
Oh, interesting. The same prompt for both.
Yes. And the discriminator's job isn't just real or fake. It's more like, given this text prompt, is the generated audio more realistic than the actual real audio sample? Or, vice versa.
Wow, okay, so it's a relative judgment.
Exactly. It's judging realism relative to another example tied to the same prompt. This makes the learning signal much stronger and more focused for both the generator and the discriminator. It really hones in on what makes audio sound right for a specific description.
That direct comparison with the same prompt seems like a really smart refinement. Okay, that's the AR. What about the C, the contrastive loss?
This is the other key piece. They added this novel contrastive loss for the discriminator. So the judge isn't just learning to tell real from fake based on the relativistic comparison.
It does something else too.
Yes. It's also trained to tell the difference between audio that correctly matches its text prompt and audio that's been paired with the wrong text prompt, like one shuffled from a different example.
Ah, so it's learning context.
Yeah.
Not just, is this plausible fire crackling audio?
Yeah.
But is this plausible fire crackling audio that actually matches the text description, fire crackling?
Precisely. It has to learn the semantic connection. Does the sound match the words? By training the discriminator to spot these mismatches, it gets much better at understanding if the generated audio is appropriate for the prompt.
And this helps with sticking to the prompt without needing CFG.
That's the idea. It improves prompt adherence naturally by making the discriminator sensitive to the text-audio relationship, rather than using the CFG technique, which, as we said, can hurt diversity. The contrastive loss helps ensure the meaning is right.
So, combining the relativistic part, judging relative realism, with this contrastive part, judging if the audio matches the text. That's how ARC gets around the problems with distillation in CFG.
That's the core innovation, yes. The relativistic loss pushes for faster, high-quality generation, while the contrastive loss ensures it stays true to the prompt, all without the baggage or the diversity limitations of the older methods.
Okay, this sounds great in theory, but how does it actually perform? This is where it gets really interesting, right? They applied it to stable audio open, you said.
Yes, they took the stable audio open model and applied ARC post-training, but they didn't stop there. They also optimized the model's architecture itself. It's based on a diffusion transformer, or DIT.
Optimized how?
They essentially made it smaller and more efficient. They reduced the internal dimensions, cut down the number of layers, added something called QK layer norm for better interaction between parts, and removed one specific input feature related to timing.
Streamlining it. Did that reduce the size much?
Significantly. The parameter count went down from over 1 billion to about 1/3 of that, a huge reduction, while they aimed to maintain performance.
Wow, okay. That's a serious diet.
It is a lot.
The speed.
The speed improvements are, frankly, stunning. On a top-tier AI chip, an H100 GPU, they reported generating about 12 seconds of high-quality stereo audio in around 75 milliseconds.
75 milliseconds. That's basically instant. Less than a blink.
Pretty much. And even on a mobile device like a modern smartphone, they got that same 12 seconds of audio down to about 7 seconds of generation time.
7 seconds on a phone. That's still incredibly fast for this kind of task.
Absolutely. The paper claims this makes ARC, as far as they know, the fastest text-to-audio model out there.
An incredible leap, definitely. But speed isn't everything. What are the quality? Did it sound good? Did it match the text? Did they trade quality for speed?
That's the crucial question. They used a bunch of objective, scientific metrics to measure this. Things like FOPNL3, KLPass, CLAP score, standard ways to evaluate audio quality and how well it matches the text. Okay?
And they also introduced a new metric, the CLAP Conditional Diversity Score, or CCDS, specifically to measure how much variety the model could produce for the same prompt.
Measuring diversity directly. Smart. And the results.
The results showed ARC is really competitive with other state-of-the-art fast methods. It holds its own on quality and prompt following, but where it really excelled was in preserving that generative diversity. It didn't collapse into producing the same sound over and over, which can happen with other acceleration techniques.
That's huge, especially for creative uses. What about human ears? Did people actually listen and compare?
They did. They ran subjective listening tests using a standard method called WebMUSHRA. People listened to audio generated by ARC and other models.
What kinds of sounds?
A real mix. Musical stuff like Latin funk drum set 115 BPM, but also everyday sounds, sports car passing by, fire crackling, water, a good range.
And what did the listeners think?
The feedback generally showed that ARC maintained really good diversity compared to other fast methods, like one called Presto. People noticed the variety. Good.
In terms of raw audio quality, sometimes the original, slower, stable audio model was rated slightly higher, which isn't too surprising. But ARC was still considered good, and the trade-off for that massive speed up and the strong diversity seems very, very favorable.
Makes sense. You also mentioned something about ping-pong sampling. Is that part of the magic?
Yeah, that's the specific technique they used during inference, the actual audio generation step with the trained ARC model.
How does it work?
It's a way to refine the audio quickly. Instead of just steadily removing noise like in standard diffusion, it kind of bounces back and forth, removing noise, adding a tiny bit back, removing more. At progressively lower noise levels, it iteratively cleans up the signal.
Okay. And why is that important?
Well, the key thing they highlight is that they can do this without using classifier-free guidance.
Avoiding CFG again.
Exactly. And skipping CFG saves a significant amount of computation and memory during generation, contributing further to the efficiency.
It really sounds like they optimize things at multiple levels. The model architecture, the training method with ARC, and the inference technique. Very thorough.
Definitely. They even draw this interesting parallel in the paper.
Oh, yeah.
Between ARC's relativistic objective, that comparison between real and generated, and how large language models are often fine-tuned for alignment using human preferences.
How so?
Because the ARC discriminator learns to prefer generated audio that's more realistic than real audio for a given prompt, it's implicitly learning a kind of reward signal, similar to how LLMs learn to produce outputs that get higher rewards based on human feedback. The discriminator acts like an implicit reward model focused on realism and prompt alignment.
Fascinating connection, thinking about quality in a relative way.
Yeah, it's a neat insight.
And they didn't just make it fast on giant servers, right? You mentioned mobile optimization, too.
That's right. They specifically worked on getting ARC to run efficiently on mobile devices. They used ARM's Kleidi AI library and a technique called dynamic int8 quantization.
Quantization. That's like using less precise numbers to save space and speed things up.
Basically, yes. It reduces the memory footprint and speeds up the calculations, often with minimal impact on quality if done carefully.
And did it work well on the phone?
Very well. They mentioned testing on a Vivo X200 Pro. The quantization and optimization cut the inference time roughly in half, from about 15 seconds down to under 7 seconds for that 12-second audio clip.
Wow.
And it also significantly reduced the RAM needed. So while 7 seconds isn't the 75 milliseconds you get on an H100...
Still, getting it under 10 seconds on a phone is a huge deal for usability.
Absolutely. It opens up possibilities for on-device generation, which is really exciting.
So with this kind of speed, both high-end and now getting towards mobile, what kind of creative doors did this actually unlock? What's the potential?
Well, the researchers seem really excited about real-time creative workflows. They mentioned doing some informal tests, like in music production and sound design, and they found that the responsiveness, getting sound back almost instantly, really changes how you interact with it. It becomes more of a conversation, sparked in ideas. You could, type slightly heavier kick drum and hear it immediately in your track.
Yeah, I can see that being transformative, like sketching with sound.
Exactly. And they also found some cool audio-to-audio tricks emerged almost for free.
Like what?
Things like style transfer, making one voice sound like another, or making generated sounds follow the rhythm of an existing beat. And they could do this just by feeding existing audio into the model as the starting noise without any extra training specifically for those tasks.
Whoa, okay. So using existing audio as a sort of template or guide.
Sort of, yeah. Using it to condition the generation process. Very versatile.
That's really neat.
Yeah.
Are there any downsides or limitations still? Anything holding it back?
The main thing they acknowledge is the model size, even after optimization. It still requires several gigabytes of memory and storage, which might still be a bit too hefty for some ultra-lightweight applications or super easy distribution, but it's a huge improvement.
Right. Still needs a reasonably capable device.
Yeah, for now.
Okay, so wrapping up this deep dive.
Yeah.
The big picture seems to be that this ARC post-training method is a pretty major step forward.
I'd say so. It makes text-to-audio generation significantly faster, pushing it towards speeds that are genuinely useful for interactive creative work.
And the key is it does this without necessarily making the audio worse or less varied, unlike some older methods. It avoids needing distillation or CFG.
That seems to be the core achievement, yeah. Speed plus quality plus diversity achieved through this novel adversarial framework.
It really gets you thinking, doesn't it? If you can generate high-quality, diverse audio from text almost instantly, how does that change things? Music creation, sound design for games, film, maybe completely new applications we haven't even thought of.
It's a great question. The potential for lowering the barrier to audio creation and enabling new forms of expression seems huge. And for anyone listening who wants to dig deeper. Yeah.
The researchers mentioned they plan to release the code, and there's already a demo website linked in the paper, so you can actually try it out.
Oh, cool. Definitely worth checking that out to get a real feel for it.
Yeah.
It feels like we're getting closer to a time when making sound could be as fluid as typing. Really exciting stuff. Thanks for unpacking all that.
My pleasure. It's always fascinating to see these fields move so quickly.